Okay, hello everyone. So let us start the class. In the last class, we were discussing this continuous dependence on the solution on the given data. So we considered two problems, one where the right hand side was f and one where the right hand side was g, and with two different initial conditions. And then the idea was that if these two functions are closed, and if these two numbers are closed, how close the solutions will be. Right? So for this we had a statement. So we assume that 1 and 2 has unique solution on interval I. So that means appropriate conditions on f and g. We can actually reformulate it by saying that f is Lipschitz continuous and distance between f and g is less than epsilon. Uh, Furthermore, if you assume that the initial data is closed, then we need to show this estimate. Okay. And importance of this estimate is that you can see that when delta is 0 and epsilon is 0, basically the values will be same. So this is proves the uniqueness also. Okay. So the continuous dependence also gives you uniqueness. But for the timing, it tells you that how much maximum change you can expect in the solution if you know the change in the right hand side and change in the initial condition. So this is a change due to the initial condition. This is the change due to the uh, this change in the right hand side. All right. So you're trying to prove this result, and we again started with the integral form of the equation. So we looked at these two solutions. This is the solution with respect to f. This is the solution with respect to g. And the initial condition for this is x1. Initial condition for this is x2. Okay. So basically we looked at the integral form of this and subtracted each one from another one. Then we got this uh, uh, integral relation for the difference. And then what we did is that we used the Lipschitz continuity of f and the fact that f and g are close. So basically we divided this f and g by subtracting f and adding f for the second solution. And because this is less than epsilon and this is less than k of these two solutions, so we got these two terms. Then we were trying to prove our estimate. So we defined something called E of t, which is basically integral of the difference between solution from t naught to t. And then we observed that if you look at this relation was nothing but this relation. Then you got this. Okay. And then what we did is that we use this integrating factor, multiply this side, and then integrate both sides. So once we integrate both sides, we got an estimate for ET. Okay. So we get the estimate for ET. This estimate for ET is given like this. Okay. So this is the estimate for ET. And now let's go forward and try to finish this proof. So far, is it clear? Is it clear so far?
Yes, sir.
Okay. So now to prove the remaining part, let us note that the distance between x t and x bar t is less than equal to, let us go back to this relation. So the first term will be this thing, and then remaining terms will be this thing. But note that this is what is this. This is exactly our E of t. Okay, so this will be delta this is delta, this is k of et. Okay, and the last term is nothing but epsilon t minus t naught. Okay, so plus epsilon t minus t naught. Okay, so this is less than equal to delta, and now we are going to multiply this with k. Okay, so that we can get this term properly. So delta plus, now you multiply k, so this will go away, so we get delta exponential k t minus t naught minus 1. Okay, plus, now again this square will go away when you do that, so plus epsilon by k. Okay, so this is minus, this is minus, and k t minus t naught plus 1. All right, plus epsilon by k exponential k t minus t naught. Okay, so now this delta will get cancelled with this delta because this will go here, and then what we get is delta exponential k t minus t naught minus, now this get cancelled, and what you get is minus epsilon t into t minus naught. Okay, and this will get cancelled with this one, so I should write this one also, epsilon t minus t naught. Okay, so that will also get cancelled, so what you get is minus, so let me precisely, this get cancelled with this one, so what you get is minus epsilon k, that's it, plus epsilon, I think this was minus of this. Okay, these both were minus, and this is okay. This is plus. Okay, epsilon by k exponential t minus t naught. Okay, so this will be equal to delta exponential k t minus t naught minus epsilon by k exponential k t minus t naught minus 1. Okay, and this is the exactly the estimate what we are trying to prove. All right, so so this is the continuous dependence, and it tells you exactly what is the maximum change you should expect due to the initial condition or due to the right hand side change. Also, this automatically implies the convergence, because if f and g are same, this will be 0, and initial conditions are same, this is 0, so the difference between the solution is 0, and that would be it. Okay, now so this was discussion about the semi-linear ODE. Now if you go to the non-linear ODE, in general there is no method. In general there is no theory. So basically the idea is to always convert them into the semi-linear case. Okay, at least locally, if you cannot do it globally. So if you can do that, then you can use this theorem. But let us look at some methods now. Methods for nonlinear equation. Nonlinear first order ODEs. Okay, so you already know all the methods, because the first year course was about methods only. So you already know what are exact equation. You already know how to what is exact equation, right? Yes, no.
Yes, sir.
So I'm going to assume that you have gone through the first year OD part, because otherwise this course becomes only the OD course, not it won't be a PD course. So the idea is to basically fill in the gaps, the whatever gaps you had left in the first year. So and that those gaps were theoretical. These were not method gaps. You already know all the methods. Okay. So basically you already know what are exact equation, and you already know what uh, if you don't have the exact equation, you can try to make them by finding integrating factor. Okay. So you should practice some things about how to solve them, and how to try to make the equation exact and then solve them. Okay, so this is fairly standard things, and you should know this by now. Okay, so all these things I am going to assume that you already know, because otherwise just I will be repeating myself. Okay, what would be, so these methods will remain the same, so you can just use that. Only thing is that the theory now it gives you the guarantee that in what you're getting is reasonable or not. Okay. So now with that understanding, let us go to the systems. So we'll try to do now the theory for the systems of ODs. Any questions so far? Any question? I will also upload some notes which has more details about what we have done, and you can try to follow the notes. Pretty much I have covered everything, and the part which is missing, which I have not covered, is basically first year part. Okay, so you can easily go through it. So let us look at system of ODs. What is system of ODs? So basically here, instead of taking scalar x, you take vector x, which will be again a function of x. So this will be a function from R, or an interval in R. So let's say I to Rn. Okay, and I is some interval in R. So t will be in R, and then x is a vector function, so it will be in somewhere in Rn. Okay. Now, in general, how it will look like? It will look like xt will have n component, x1t, xnt. Okay, and so of course this will be in Rn. And now let us define a function f, again a vector function, from I cross Rn to Rn. Okay, so what will be f? F will be basically a function of scalar t and vector x. So this, and of course it will have n components, so each will be a function of t and vector x. If you want to write it in a more general way, you can write it f1 t x1 xn, and similarly fn t x1 xn. Okay, this is more general way. Of course it's in R. Then we can do the component wise differentiation, and we can write that x1 prime will be f1. Similarly, x2 prime is equal to f2, where f1, f2, fn are given function. Similarly, xn prime will be fn t comma x. Okay. It's now often practice, if everything is well defined, then we can convert into system representation. So how to write it in systems representation? So, and this is easier to do, you just write vector x prime is equal to vector f. So other than these arrows, nothing changed. It looks exactly like the scalar case. Only thing is that you should understand what is this derivative. This will be basically component wise derivative. Okay, so this you have to understood in that way. Now, so now we are looking at the ODE of this one. And our aim is to study existence, uniqueness, and well-posedness of the corresponding initial value. What will be the corresponding initial value problem? That means the vector x at some t naught is given as a fixed vector. Let's call it A. More precisely, x1 at t naught is equal to A1, x2 at t naught is equal to A2, and so on and so forth. So xn at t naught is equal to an. All right. So basically, we'll be interested in studying well-posedness of this problem. Okay, this is not the fully nonlinear system. It's again a semi-linear system, but again, even for the scalar, we don't have the general theory for the completely nonlinear equation. We have only for the semi-linear case. So this is what we are going to study. Now, before we go further, there is an issue. Note that in the study so far, we had this maximum node. So if a scalar function, let's say x, and you have another scalar y, then you know what is this. This is basically nothing but the absolute value, right? If you have two scalar values x and y, so these both are in R, then you know what is this. This is absolute value, right? Absolute value of x minus y. But this is not the same when you go to vectors. So if you take two vector x and y, what should be this norm? Okay, norm means what should be this distance between these two vectors. When you have two numbers, you know what is the distance between them. You subtract one from another, take the absolute value. When you have two vectors, it's not very clear what is the distance between them. There is no unique way to represent this distance. There are some way which you already know. For example, if you have vector x and y in Rn, then standard one is Euclidean, is called Euclidean norm, and this is the most famous one. Basically, is represented with this 2. This will be square root of x1 minus y1 square xn minus yn square. Right, all of you are seeing this. This is also called distance norm. Basically, it represents the distance in this xy space between these 2 points. Agree? All of you have seen this, right?
Yes, sir.
Yes, sir.
Yes. But this is not a unique way of doing it, because I can easily replace this 2 with a p bigger than 1. For any p bigger than 1 and less than infinity, that this you can have something called p norm. This is called p norm, and you can, instead of taking square root, you will take 1 upon p, but here you will take x1 minus y1 square. In fact, this is also true for 1 also, so not square, p xn minus yn p 1 upon p. Okay, so this is also has the same property as the above distance. So this is also a norm. You already know what is a norm. The definition of norm is given to you, right? You already know what is the norm?
Yes, sir.
Yeah, because in the linear algebra, remember when we taught you inner product, and then we showed that some inner products are norms. Not all the inner products are norm. No, I'm sorry, all the inner product induces a norm, but not all the norms are from the inner product. Okay, so that way this is from the inner product, which is basically dot product. These are, if p is not equal to 2, then they are not from, no, they are not from any inner, they are not induced by any inner product, because the parallelogram law has to hold for that. For if you have norm, and if you want to show that whether it's induced by inner product or not, there is a theorem saying that the parallelogram law has to hold, and then it will hold. It will be induced by inner product, and that can you can check later on, because this is not the point. But my point is that there is no unique way. The another quite interesting one, which you should know, are basically for p equal to 1, what you will have is 1. This will be basically x1 minus y1 plus x2 minus y2 and xn minus yn. So you just sum up component wise distance. The another one is called infinity norm. This is maximum over I of xi minus y. Okay, now there's, so you can see that there are several of them. Okay, there are infinitely many of them. Good thing is that, what is a good thing? The calculus is same in all of them. That means if the convergence is, if you converge in one norm, if for example if you converge in two norms, you will always converge in all the norms. Okay, so for the calculus part, it won't make much difference other than when you're trying to take derivative of the norm. Here you can take derivative of two norm or p norm, but you cannot take derivative of one norm because of absolute, it is not differentiable. Okay, so other than this part, the theory is exactly same. So it won't matter for our discussion, where we never take the derivative of the norm, is that what norm we take between these two vectors. So I will just say it's a vector norm. I won't even mention which norm it is. Because if it's hold in one, it will always hold in another one. Okay, so the unless if there is something weird, I will tell you, but there is nothing in this, at least for the ODE theory. Okay, so if that is clear, then what we can do is that we can try to define rectangles in Rn or Rn plus 1. Okay, so let us look at the rectangle R, which is in I cross Rn. Okay, because this is what we needed in the scalar case, right? We had a point in T naught, and we had a point x naught, which was in R, but here it will be a vector x naught, which is in Rn, and then we'll try to define a rectangle. So the rectangle here will be exactly the same. It will be the point t comma x such that distance between t, this is less than a, so this is the normal, and the distance between vector x and x naught, again x naught is a vector now, is less than equal to b. Now it doesn't matter which norm it is, but note that the rectangles will be different. If the norm is different, the rectangle will be different, but the theory will hold on that rectangle. So that you should keep that in mind. So for some a comma b comma positive. All right. So this is how a rectangle in Rn plus 1 will look like. I cross Rn. Yes, any question? Okay. So if there is no question, we can go ahead. So with that, let us try to give the statement for the local existence and uniqueness, and the proof is fairly straightforward. In fact, there is no need to give the proof, as I will explain you in a second. Okay. Before we go forward, let us say what do you mean by Lipschitz continuity here. Okay. So take a vector f, a vector function f from I cross Rn to Rn is said to be Lipschitz continuous. Again, whether it's local at point or whatever globally, it's the same thing, the same definitions hold, but I'll just say local continuous in x, in vector x, in the second variable, if f is continuous. Now the continuity in Rn to Rn is known to you, right? And there exists L positive such that the distance now whatever that distance is doesn't matter, but it has to be the same distance here. So this norm and this norm has to be same. You cannot switch in between. So once I fix a norm, I can fix any norm I want, but once I fixed it, it will be the same norm in Rn. Okay, you cannot change in between, otherwise you'll get some constant out. You have to take care of those constants. You can still do it, but you have to take care of the constant. Okay. So we say f is Lipschitz continuous with respect to x if this inequality hold, and you can see that this is exactly the same what we did in the scalar case. Only thing is that I am replacing this with vectors, and because I am replacing these with vectors, I am forced to replace this with the vector norm. That is the only change. There is no other change. If you understood that, then we have local existence theorem. And the statement is exactly the same, but this time the statement is in rectangle in Rn plus 1. Okay. So let f be a continuous vector valued function. Okay, because vector valued because it's a vector defined on R. Again, so to distinguish between the 1D in the scalar and the vector, I'm just writing these norms. Okay, you don't even have to write this. It will be clear from the context what it is. Okay, so but just to clarify things, I'm writing it here. So define on this R for some a comma b positive, and it's continuous. And suppose F is Lipschitz continuous on R with respect to second variable. So second variable is a vector x. Then the solution will exist in a neighborhood of T naught. And what is that neighborhood? It's exactly T naught by T naught less than equal to H. H is basically minimum of A comma B by M. What is M? M is basically maximum or R of the function mod T comma X. Okay. And what is the proof? Proof is exactly the same. Only thing is that this time instead of dealing with integral equation, we'll deal with the vector integral equation. So, okay, then the IVP has a solution. Has a unique solution basically. And what will be the IVP? Just to complete the statement, IVP is x prime is equal to f t comma x, x at t naught is equal to x naught. Okay. All right. So now,
So what was M in the previous?
it's a maximum of function f. So yeah, you can take the norm. You have to take the norm. You're right.
Okay.
Whatever that norm you are dealing here, it will be the same. And the proof, I'll just give you some idea, and it's a copy paste from the scalar case. Only thing is that we look at the Picard iterations here. Once I define the Picard iteration, the proof is exactly the same. So what will be the Picard iterations here? The Picard iteration will be basically you define, let us call it x vector x 0. This is basically x0 itself. So that's why there's no need to write separate notation, but this looks weird. So let us define x k plus 1 t will be basically the initial condition plus t naught to t vector f s x ks ds. Okay. Now all these things should make sense to you. This is a vector, this is a vector, output here will be a vector, so you can add them, and this will, you can compare them with another vector. Okay, so this is a equality. So this is vector integral equation. Following the exactly the same line of proof, you can show that these sequence of functions, the sequence of vector functions, converges uniformly to a vector xt. Okay. And of course, when you say converges uniformly, there in the definition of uniform convergence, wherever you had xt, you'll replace it, mode of xt, you replace it with the norm, appropriate norm. Replace absolute value with norm, same norm, whatever. Then you get convergence and blah blah blah. All the arguments are exactly the same. There is absolutely no difference. No difference at all. It just goes through. Only thing is that keep putting the arrow on the top of x and replace the absolute value with the norms wherever you have vectors. Okay, so the proof is over. So it's a good time to recall that proof also. Here again you should note that you have a Lipschitz continuous L. Lipschitz continuous that L will appear and you will get a similar estimate. You have to basically show that they are uniformly Cauchy and then do the use the completeness argument to get the x vector x. Similarly, you can repeat the same thing for global existence. No difference in proof. Same as scalar case. Only difference is the step you took. So the step, the set what we took there, it was t minus t naught less than a, and for all x in R. Now this will be for all vector x in R. On this, if f is continuous, sorry, f is Lipschitz continuous, so it will be global Lipschitz with respect to second variable. That's what it means. This implies global solution on this strip. We're calling it strip, but it's in Rn, right? Note that. So it's in Rn plus 1. So if you want to draw, we can draw. So how this strip looks like? So basically something like this. Okay. So this will be basically T, and this will be Rn. So this is x direction basically, but I'm writing Rn. This is R. So this is t minus t naught less than a, and then the remaining part is this. Okay, so this is how that's why we call it strip. All right, so now again what is left is a continuous dependence, and again the proof is same. So continuous dependence proof is exactly same. Okay. Any questions so far? Any questions so far? All right. So if there is no questions, we go forward and make it a little bit more useful by looking at the linear systems. All right. So how we go about it? So how the linear systems will look like? The linear system have a standard form, something like xt is equal to at xt plus some gt. This is a matrix. So if you want, I can write like this. It's a matrix. So this is a matrix vector multiplication. This is a vector. This is a vector. So of course I have to take the derivative here. So this is a vector equal to this vector plus this vector. A because it's a matrix which is a function of t, will be something like a11t, a12t, a1 and t, an and t. All right. Now, how would we argue about existence and uniqueness for this problem? The thing is very easy. Why it's very easy? Because note that if you take an interval in t, something like this, and let's call it I, then if aij's are continuous on I, this implies that if we write it in the form of the nonlinear system, f will be Lipschitz continuous. Is this statement clear to you? Is this
No,
statement
sir.
clear?
Can you explain again?
Okay. Good. So what let us look at okay. So let us look at f t comma x minus f t comma y. Okay. This will be a t x minus a t y. Agree? Or not infinity, some. Agree?
Yes, sir.
Okay. Then there is nothing left. Not that every okay. So there are several ways to do it. The easiest way is the following. Because all the components of A are continuous, so AT are continuous, so AT is also a continuous mapping. Huh? Okay, so it will be n cross n matrix, so it will be a continuous mapping, means A will be basically going from I to Rn cross n. So it will be bounded in this n cross n, it will be bounded, so you can write it less than equal to norm of A t x minus 1. What is this? This is norm of A in n cross n. And why I'm writing the same norm here, You know the matrix norm induced by a vector? Have you seen that? Have you seen this? Matrix norm induced by a vector norm?
No, sir.
Okay.
No, sir.
Okay. So I'll explain. In fact, that is also not needed, but one can either way you can do it. It's not important. But for example, one way you can easily do it, because each mode of A is bounded, because aij's are continuous. So aij's will also be bounded, because it's a closed bounded interval. So this implies that I can take I can so let's write it properly. Here I can write L. I'm trying to avoid that matrix now, but okay. I can write L here, where L is maximum or Mij. Mij is basically maximum of Aij T over I. Now is this fine? Yes?
sir.
This is okay. So by doing this, I have avoided the discussion about the matrix norm induced by a vector, because that will be again new topic. So the point is that because AIJs are continuous, so if you look at the partial derivative of you look at the Jacobian matrix of this function. So this is nothing but Aij, right? Okay, and each one is bounded. So you can take the maximum of all of them and they're bounded. Okay, this is roughly what I'm doing. And note that this is nothing but a Lipschitz bound if you compare it with the 1D case. Right? There, if the partial derivative with respect to x exists and it's bounded, we say it's Lipschitz continuous, right? Here we are doing it for each component in f and x. So if that is true, then this is also the case. Okay. So in this case, this happens to be the situation because everything is linear with respect to components of x. Alright, so because it's Lipschitz, you will have unique solutions. Okay, so that means I can have a statement about the unique solution and then we'll stop. So let's consider this ODE, which is a linear system. Okay. Now, if x naught is some vector in Rn, then there exists a unique solution to IVP. Okay, before if this is x naught in Rn and Aij's are continuous on I, then x prime okay, this IVP has unique solution. Okay, so it's fairly easy, straightforward in this way. This becomes a subcase of the other. On I, of course, I have to say unique solution on I don't know anything outside I, so I cannot say. So if Aij happens to be continuous over the whole thing, then that is the case. Then there will be, completely you'll get a solution for entity, unique solution for entity. Now in the next class, before you come to the next class, which is I think on Friday, tomorrow we have holiday, right? Yes or no?
Yes, sir.
Okay. Yes, sir. So before you come to the next class, please read the Wronskian and the existence and uniqueness theory taught to you in the first year course of ODE about the linear higher order equations and the linear systems. Then we can wrap it up in 1 or 2 classes. That is covered to you, right? Wronskian and the linear independence of the solution and the general solution form is covered for you in the first year course. So go through that, because I will mention it, but I will not prove it because this is already proved. So I'll go through really fast. So the proofs are there. So this will be assumed that you know the proof. You cannot claim that, sir, आपने class में notes में नहीं है. That is already known to you. We'll use that information. We cannot keep repeating that information. So please go through that. So you are all on the fresh mind. Go through the Wronskian linear independence and for how you arrive at a general form of the solution. Remember that to get the general form of the solution for the higher order ODE. So if you do it for the second order ODE, that should be enough. So even for the second order ODE, you needed existence and uniqueness of the IVP, and this is what we have proved today. So we have done a patch-up job here. So the methods are covered there, the theory is being covered here. So you go through the methods again, and then we can go through those methods relatively fast. Okay. So we'll meet on Friday, and then we'll try to wrap up this theory part of at least the higher order equation and the linear system of equations. I'll add some other things if needed. All right. So I'll see you on Friday. I'm stopping the recording and I'll stay here for some time if you have some questions.